All right, one more concept for us to cover from chapter 3, and that concept is pressure. So pressure for us is going to be the ratio of force to area on which the force is acting. And it's going to have units of newtons per meter squared, not meter cubed. And that's going to have units of P, and that should be a little a, which is a Pascal. So that's what we're going to see in terms of force. So remember, pressure is force divided by area. So you may have seen the equation P equals F over A before, and that's pressure. Knowing a Pascal is a Newton per meter squared could help you check your work. So remember, sometimes we can multiply and we can divide units and we might get something like a Newton per meter squared. And remembering that it's a Pascal could be very helpful for us going on. So most of the time when we talk about pressure, we're talking about fluid pressure, especially as environmental engineers, because we deal with fluid mechanics, we deal with pipes and air and water and all those good things. And fluid pressure is defined by the force that's exerted on what we call a frictionless plug to keep the fluid from emerging from a hole. So this is kind of the standard classical definition that a textbook would give you. So if we have in this diagram here, fluid moving through a pipe or some kind of container, if we put this little plug in here and we assume that this plug is frictionless, the pressure is the force that's exerted against that plug. And that's how we could define fluid pressure very classically from physics, thermodynamics, that kind of thing. But for our purposes, we want to talk a little bit more specific about some aspects of pressure that are going to be related to what we do as environmental engineers. So let's say that we have this vertical column of fluid that we see over here, and that the fluid has a density of rho, which is in terms of kilograms per meter cubed. There's an external pressure P sub 0 that is exerted on the system. That's what's up here at the very top. Now, if we are looking for what is the pressure at the very bottom of a specific column, that's what we call hydrostatic pressure. And hydrostatic pressure that's exerted at the base is going to be equal to rho, which is the density, times the gravitational constant g, times h, which is going to be the height of that specific column of fluid that we have. And that H also has a name. Sometimes we call this the head of a particular fluid, and that's the height of basically a hypothetical column of fluid, and what basically that would exert at a given pressure at its base, if the pressure at the top was equal to 0. And so you'll see head a lot more when you get to fluid mechanics, or if you have taken fluid mechanics in the past, but just be aware that that is going to be a common term that you start to see in future classes. And basically what we're going to say is the pressure at the bottom of that specific surface down here at the bottom is going to be whatever pressure is exerted at the top plus whatever hydrostatic pressure is exerted at the bottom. So the total pressure in many systems when we're talking about fluids is the external pressure plus the hydrostatic pressure. So a quick little aside, why would we care about head or pressure in environmental engineering? Well, for us specifically, one thing that's really important is that we use a lot of pumps. So head pressure in pumps is very important for water and wastewater operations. So having a specific amount of head available is important. In fluid mechanics and hydrology, how far water flows and how it flows in channel and pressure devices depends on different pressures. And then things like hydropower and geothermal. So in order to transfer power from turbines to electrical storage units, we have to be aware of pressure. So this is going to come up over and over again. We're going to review this concept now, and then we're going to see it start to pop up later during the semester, especially as we talk about different pressures of gases and different fluids and things like that. So to finish this out for this particular lecture, I want to pop this example up onto the screen, and I will put the solution to this problem in a different set of videos for you. But we want to know what the pressure is 30 meters below the surface of a lake. And we can assume atmospheric pressure is 101,325 pascals, and the density of water is 1,000 kilograms per meter cubed, and we know what G is. So take a pause and see if you can figure this out. And if you have trouble with it, the next slide is going to have some hints to maybe help you try this problem again. So last thing that we want to talk about with pressure is the difference between atmospheric, absolute, and gauge pressure. So these are all slightly different terms, but they are important. So atmospheric pressure is going to be the pressure that we see at sea level, and we can call this standard pressure many times, and that is 1 atm or 1 atmosphere. It's the same as 760 milligrams of mercury, and that's just another pressure unit for us. We have conversion tables that are in the very front of your textbook. They are also provided to you on Canvas to convert between things, so just be aware of that. We see many different units for pressure. And then everything so far that we've been talking about is absolute pressure. It's both the pressure of the atmosphere and external gauge pressures. Pressure of 0 is what we would call a perfect vacuum. So that would be if there is no atmospheric pressure and no gauge pressure in the system. So gauge pressure is what most of our devices are going to measure, and that's the pressure relative to atmospheric pressure. So atmospheric pressure is kind of our baseline, and then any of our devices are going to measure gauge pressure, which is pressure above and beyond that atmospheric pressure. If gauge pressure is equal to 0, then absolute pressure is going to equal atmospheric pressure. So normally what we write when we talk about pressure is we say that absolute pressure is the atmospheric pressure plus the gauge pressure, and that if gauge pressure is equal to 0, then the atmospheric pressure is our absolute pressure in the system. So everything that we've talked about on the previous slides is the total pressure, it's the absolute pressure in the system, and maybe that'll help you to think about that example if you had any questions on it. That's going to wrap us up for pressure. Make sure to check out the solution to example 3.4 if you had any problems solving that problem.